All right. Good afternoon, everyone, and welcome to Epinic e-learning web class. We will be doing IPv4 to IPv6 transition, and today is the 6th of March 2013. So, when I talk about IPv4 to IPv6 transition, what we'll be discussing all about how you can migrate your network from up and running v4 network to IPv6 network, right? As you all know, IPv6 is a new protocol. Since IPv6 is already in place since like 10, at least 10 years, but still it is very new in the deployment because most of the big ISPs, network operators, they haven't deployed IPv6 into their network. But very recently, since we have IPv4 address crisis, then people start deploying IPv6 towards the very uh, late of 2010 and early 2012. In this time, people are getting very active to deploy IPv6 into the network. So when we talk about IPv4 and IPv6 protocol, the very fundamental concept is the V4 and V6 are completely two different protocols. They are not backward forward compatible. What does that mean by? If you are running any server or any machine on IPv4 protocol and another machine, either a server or a client running on IPv6 protocol, those two machines cannot communicate. Simple as that. It's a two different language. So if two persons speaking in two different language, they cannot communicate. Same concept in IPv4 and IPv6. Then the question is, if those two protocols are not compatible to each other, then in the real internet we have a mix of both V4 and V6 running computer, right? How they can communicate, what would be the transition technologies, like how can build the internet effectively so that two different protocols can work together. Those are the things actually we'll be discussing in this module, IPv4 to IPv6 transition. Make sense? A little bit of introduction about myself. My name is Nurul Islam Roman. I'm the senior training specialist in APNIC. So my role is to kind of do technical workshop, presentation, a tutorial for APNIC members, engineers, and this is how we try to transfer that required knowledge that can help them to build and operate effectively in Asia Pacific. Okay, so we have sort of an FAQ in our website, which is www.apnic.net/elearning support. It's worth having a look if you face any difficulties, any technical problem when you are watching this webcast. So all those very common problems are outlined on this FAQ. So if you're having any issues, it's worth having a look. And then when we will finish the presentation today, we'll be show you that URL that you can use to give us some feedback. So your feedback is very, very important for us, and this is how we try to kind of improve our future e-learning session or any other like session that we'll be doing in future. And we will also would like to acknowledge Cisco systems because they help us to kind of build content on those transition technologies. Okay, we'll move forward. So transition overview. So if you see the internet and when people are deploying IPv6 into the internet, there is a terminology called native v6 or native connectivity, right? And there is another concept of IPv6 is getting transit via v4 tunnel, right? So pretty much in the internet industry, we have the native v6 some places, and we have tunnel. So those are the two basic things that we'll be discussing. Apart from that, like there is another concept called translation. We'll be trying to discuss a little bit of translation as well when we do the transition technologies. But all the transition technologies that we have currently, those are really transable transition technologies, fall under those three categories, either native, tunnel, or translation. Okay, as I said, IPv6 is very new in terms of deployment in the real network or the commercial network. So that is why we consider IPv6 deployments or IPv6 only deployments are very rare at this stage. What does it mean by IPv6 only deployment? It means in a machine, either as a server or as a client, they only have IPv6, no IPv4. That's what we call IPv4 native. And as you can see, V6 only deployment is very, very rare. In practical reality, what we can see into the industry? So in the industry, we can see some machines or most of the machines that are connected to the internet are running on IPv4 protocol. Since V4 protocol address is running out, so we have a new protocol address called IPv6. So the new machine, either as a client or as a server, when they will come and join into the internet, the option, the very first option that we have, give them IPv6 address, right? So when you give them IPv6 address, then those machine, the new machine will be running on IPv4 only. Then there will be a situation where the old machine running on V4 and new machines running on V6, there will be an incompatibility issues. They cannot communicate, right? And now we should have an option to solve this incompatibility problem. So that is why we have the transition technology, and this is what the practical reality in the industry now. So IETF, Internet Engineering Task Force, they are the forum actually who works on developing internet standards, right? So that if the vendor or when the vendor develop their product based on that IETF standard, we expect those devices will work in a multi-vendor environment, right? So that is what the purpose of IETF, they develop the standards. So in IETF, in relation to IPv6 transition technologies, there are three main working groups working on those transition technologies. So namely V6 Ops. So V6 Ops is in a working group, right? Then they actually define the process, like what would be the process, like to move from V4 to V6. So they discuss about those process related things. Then we have Behave, another working group. So Behave working group, they actually work on developing some solution based on the scenarios. What could be the solution in WiMAX environment? What could be solution for DSL environment, right? So those sort of things Behave working group does. And then Softwares, what Softwares groups does? So they actually look after or deal with the nitty-gritty protocol level things. What could be the protocol control level information, right? All sort of codings, there are. So those are the three main working groups that we have in IETF who are actually working on the transition technologies. Okay, so to get that idea how we can understand those transition technologies in a real environment, I'll just bring a very simplified topology of the current internet and try to see whether you can explain the situation and how we can think about the fundamental transition concepts. So in this diagram, what we have like four networks. One, let me just grab the pen tools. Yep, this is what one network. There is another network. There is another one, and there is another one. If you consider internet like this on the slide, so there are four networks are interconnected by using all those routers in here, right? Did you see? So on the edge, we have the devices who are servers, those who host content or probably access content. So those are the end system devices or the edge devices. We usually call them internet host. And as an internet host, they can be a server or they can be a client. If you see the real environment, most of the hosts connected to the internet are client. Some of the hosts are servers, those who are serving the content to the clients, right? And within the infrastructure, the intermediate system, all those routers, their job is to just carry those data from one side of the network to the other side. Be very specific, from client to servers to carry those data, right? So this is what kind of an internet topology now we have. So in this sort of topology, what we have, all those machines, if you see the black box on top of every machine, even on the routers there is a black circle. So this is what we call all those devices, either the end system device or intermediate system devices. they understand a protocol called IPv4 protocol. So all those servers, they have IPv4 protocol installed, right? They have an IP address, either private or public. I'm not going to that, complicacy, because you all know that. So what happens when those IP addresses are configured or network protocols have been configured? Then those routers that build a routing table, right? On that routing table, they have the destination address. So when packet in V4, right? When packet in V4 from this side want to go to the other side, that packet comes to the router do the routing table lookup, forward to the next destination, and from next router it goes to the other router, and this is how it goes to the other side of the network, right? And at this stage, internet was working fine, but we have some scalability problem. What scalability problem? The way internet is growing, right? We are running out of IPv4 address, the global addresses that we have, so that we can't build new servers. So, for example, we can't add new clients. There is a technique, right? We can use, but those are vendor-specific techniques that we have, like NATs and others. So, but to have a scalable solution, and we need to have a kind of end-to-end network to be built for the future internet, we need global IP address, right? And V4 cannot give us enough global IPv4 address. V6 can, the way it is in structure. So at this stage, what we did, because of the scalability problem, we have introduced the new operating system, install the new operating system on the network. That's why all those machines now become green as well. So it has got two protocols, both V4 and V6. That is why all those machines that you can see has got both black box and green box. So at this stage, when A6 want to communicate with B6, right, the packet itself, so when A created the packet, machine A created this packet with source A6, destination B6, the packet comes to the next router or the nearest router. The nearest router doesn't have any understanding what this packet means, because the nearest router only understands IPv4 protocol. So what it will do? Just discard the packet, right? So this is how the V6 transport from source to destination is not working. So what do we do the next stage? All right, let's make that router dual stack. So it supports both V4 and V6. Now the router has got two routing table, one for V4 and one for V6, completely separated, like V4 and V6 are two different protocols or two different routing table. So now when the packet from A6 comes to the router R4 or V4, R1 V4 I would say, then what will happen? That router will have a match in his routing table for the packet to be forwarded. But the next router doesn't have any match and doesn't have any routing table yet. So what the next router will do? They'll discard it. So this is what the situation that we had like 2-3 years before. Probably the ISP support IPv6, their router support IPv6, but their upstream ISPs, those who are the tier 1, tier 2, they don't support IPv6. No V6 transit available. Right? So what is the option? What we can do? We have a technique called tunneling. How the tunneling works? From this router R1 V4, we can create a tunnel up to R5 V4. What does that tunneling means? The V6 packet that machine is creating, this V6 green packet, router R1, they will add a header on top, and that header is a V4 header, right? When router 1 added the V4 header, then you will see from the tunnel source up to the tunnel destination, the routing will be done on the V4 header. When it goes to the other side of the network using V4 header, then this router will strip off that V4 header and then forward the packet natively to the host using IPv6. So this is what pretty much the basic concept of tunneling. Make sense? Okay. So this tunneling concept that we discussed so far also has got some scalability issues. What scalability issues? Okay, in that case, on the slide we have only 2 network or 4 network. We can create 2 or 4 tunnels. But what if in the global internet we have thousands of networks? Should I create thousands of tunnels to different part of the world? Probably not. That is not scalable solution. So that is why we have a concept of tunnel brokers. So what tunnel brokers? Everyone around the network or around the internet, instead of going to add a tunnel with a different individual network, let's go and create tunnel with a single organization. Everyone go and terminate their tunnel onto the single organization. And this is how we can have a sort of hub and spoke type of topology where the tunnel broker can aggregate all V6 tunnel and they can distribute prefix to the other side of the tunnel. Right? So this is what the concept of tunneling. Make sense? Any questions so far? So if you have any question, so I would suggest you to raise your hand and ask the question on the chat box anytime you want. You don't need to wait till the end of the presentation. Okay? I'll try to just pick your question and try to answer it. All right. So this is what the situation that we saw now. But in future, what we'll be doing at one stage, what we'll be doing, we will be kind of building a native V6. So all the machine when we can build as a dual stack machine, then at some point of time we will notice that we don't have any V4 traffic on the network because most of all the machines that understand IPv6, right? So V4 will be phased out automatically. We don't have any ETA like when it can be happening. I don't know. It could be 10 years, it could be 20 years, or it could be 5 years. I don't know. Depending on the way V6 is moving forward. Okay, there is a question in here: how to solve 1,000 tunnels? Well, that's what I said. That's what I said. You have a tunnel broker, so go and add a tunnel with the tunnel broker, and tunnel broker they will solve the 1,000 tunnel because they have got the heaps. I mean, this scalable equipment to handle thousands of tunnels, or they have different techniques or technologies to kind of distribute all those tunnels in different locations, different ports. Okay, but from your side, you just create only one tunnel up to the tunnel broker. All right, so IPv4 to IPv6 transition. So, as I said, there is no fixed date. We can tell on that particular day everything will be converted to IPv6 or migrated to IPv6. We can't tell that because there are million computers IPv4 running on IPv4, and when we need to convert them, it's a big job. So we have to do it very slowly, like so that up and running the current network, we are not breaking it. Still, internet works, and we can go for the migration. These are the things we need to consider. So, as I said, if I summarize all the tunneling or the transition technologies, they actually fall under three different categories. Number one category is, as I said, dual stack technique. Dual stack means every machine they understand both V4 and V6. That's what we call dual stack, right? Then we'll have tunneling technique. So, what tunneling technique? As I said, use IPv4 right header on top of V6 header, and as long as transit doesn't support IPv6, you can use V4 header to get the transit across the network. And translation technique, there will be a device in the middle between IPv4 and IPv6 host, and they can translate back and forward, right? So this is what three type of transition technology that we can use. In dual stack approach, your application will determine what will be your preferred transport. Is it V4 or V6? Mostly, it depends on the OS implementation, and application will determine. So normally they support V6 as a preferred transport. But the recent OS implementation, they don't rely on V6 transport. There are some issues, so that's why they just select which transport works better in terms of the latency, delay, and also other things. So in terms of layer 2, no big change, same data link layer, we can use Ethernet, right? Only the difference is the frame protocol ID, right? V4 and V6, that's it. There are some challenges in dual stack. So for example, if we run a dual stack network, in our IP core network, if we have IGP as OSPF, we need new version of OSPF, which is OSPF version 3. So, and then the business process, traffic monitoring, end user deployment, all are big challenges. So like if you have your access network in WiMAX 3G, right? In your control plane, in your data plane, do you have v6 support? In your network management, monitoring, OSS, do you have v6 support? Because those areas are heavily customized, the OSS, operation and system support software, right? So those are the big challenges that we have in dual stack deployment. Sometimes in the telco network, when they have RF, radio frequency on the access side, they don't want to deploy dual stack because they always would like to kind of deploy very lightweight devices. Dual stack is a heavyweight device. We have to carry so many signals because one v4 and one v6. So they prefer only one, either v4 or v6. So dual stack has got some challenges on that side as well. Dual stack and DNS. DNS plays a very significant role in terms of what transport your machine will use between source and destination. If your machine cannot resolve any quad A record, it means IPv6 address record for your host, say for example www.a.com. If this is the host name, your machine will go to the local DNS server, ask for a quad A record. If there is no quad A record on the local DNS server cache, they'll go to the root server, and from root it goes to the delegated name server, and from the delegated name server, we'll try to ask the quad A record of www.a.com. If there is no quad A record on that delegated name server, it will revert back to v4. And then when it revert back to v4 and the DNS server return v4 address, then no way source and destination they can use v6 as a transport, because as a quad A record, the quad A record is not there, they return A record, so they only can use v4 as a transport. So those are the very important part of DNS and how DNS can dictate the transport from source to destination. Okay. Any questions so far about DNS? If we see an example how the query happen, so when the query goes to the local DNS server for the quad A record, and if the DNS server has got the quad A record existing, they will respond with the quad A record. If it doesn't have, it will reply non-existence. When it reply with a non-existent, then what client will do, they will send a query for A record, and then when A record comes, they will browse or they will initiate or they'll create the session on IPv4 as a transport. Make sense? Okay. Now we'll discuss about the configuration of dual stack. How you can configure dual stack. That's very easy, right? How you configure? So for example, if we see the configuration on a router, just go to your router. You need to enable IPv6 unicast routing. It's a Cisco specific command in iOS based. So make sure the router you are using v6 protocol is enabled on that router. On Cisco iOS, the command is IPv6 unicast routing. As the default, this command is not activated. If you want to forward v6 packet across the router, you need to execute this command from the global mode. Then afterward, if you go into interface mode, then you can add your IPv6 address on the interface. The command is very similar as IPv4. Just syntax is IPv6 address and your v6 address. That's it. So this is how you can build a dual stack machine. So on the dual stack machine, the router now understands both v4 and v6 protocol, right? So when packet comes to the router as a v4 packet, they'll process it on the v4 routing table. If the packet comes as a v6, it will process on the v6 fib table. That's how it works. Now we'll discuss about tunneling. You see, the tunneling concept that we discussed, we can have a number of different type of tunnels. The very easy one is our manually configured tunnel. What is a manually configured tunnel? So in a manually configured tunnel, the definition is both sides of the tunnel need to be configured manually. If I want to see the data flow in manually configured tunnel, when the tunnel will be created or tunnel packet will be created on the router in a very specific terms or language, we call it when the tunnel encapsulation process will be happening on the router. So on the encapsulation process, on the v4 header, tunnel source is already configured on the router, so router don't need to discover tunnel source. They'll just look into the configuration and take the tunnel source configuration, and as well as tunnel destination is also configured on that router. So router don't need to discover any tunnel source or tunnel destination. They just take the configuration that you already put on the router as a tunnel source and tunnel destination and create the encapsulated packet. The packet will go across, right? So the definition of manual tunnel is tunnel source and tunnel destination is manually configured. Makes sense? Like the way you create GRE tunnel, the way you create IPv6 tunnel, right? Same. So tunnel source is configured manually, tunnel destination is configured manually. Then we'll discuss about semi-automated tunnel. What is semi-automated tunnel? So in semi-automated tunnel, we configure our side of the tunnel, and if you notice carefully, tunnel source is my router, tunnel destination is tunnel broker's router, right? So when tunnel broker router is the destination, then through that tunnel, my V6 packet can go across the tunnel broker and go other side of the network, right? So in my tunnel configuration, I haven't specified other side of the network as tunnel destination. I specified tunnel broker side as a tunnel destination. That's what we call semi-automated tunnel, right? So other side will be discovered by the tunnel broker. If on the other side they have a native routing or tunnel routing, depending on the tunnel broker how they manage it. So that's what we call semi-automated tunnel. In automatic tunnel, tunnel source is specified, but tunnel destination is not specified. Tunnel destination, you don't know what is tunnel destination. You ask the router, so I don't have the tunnel destination, can you discover it, right? So router has got some sort of intelligence. They will go and check what could be the optimal tunnel destination so that I can forward the packet to. So then when they discover the tunnel destination, they will put the tunnel destination on the encapsulation header. Make sense? So as an automatic tunnel, we have two examples in here today. 624 is one example of automatic tunnel, or 6RD, rapid deployment, is another example of automatic tunnel. Okay, any questions so far? No? Okay. Yeah, so I have already explained when you need the tunnel. Part of your network is IPv6 enabled and another part is not, right? And tunnel can be a manual tunnel can be a manual tunnel, tunnel can be an automated tunnel and semi-automated tunnel, right? The way you configure it. Let's see the definition and how it works. Okay, manual tunnel. Simple as that. We have IPv6 on this side, we have IPv6 on the other side. In the middle, this backbone is IPv4. They don't support IPv6. If you don't have any tunnel, what is the consequence? This packet comes here and in here it will be dropped, right? Unless we can encapsulate V4 header on top of V6 header, and this part of the network can use that encapsulated V4 header for the routing in between, and from there native V6 can go outside, right? So that is what the concept of tunneling. So in this tunneling, how we configure it? We configure this router and the other router. So this router will do the encapsulation process. What does that mean? V6 packet will be encapsulated with the V4 packet, go across the network. On this side, we will have a decapsulation process. On the decapsulation process, how it works? V4 packet header will be stripped out. The native V6 will be forwarded on the other side of the network. So that is what we call encapsulation process and decapsulation process in the tunnel. So tunnel encapsulation, I want to explain those things. Just see some configuration example. Yeah, this is what the configuration example. How we configure tunnel. On router 1, if you see router 1, it has to be a dual stack router. Router 2 also has to be a dual stack router. It means they support both V4 and V6. In the middle, I have V4, doesn't matter, right? So on that dual stack router, which is tunnel source, what we do, this machine, say WAN interface, or probably loopback, doesn't matter, it could be WAN, most of the time it's WAN. Address is 192.168.99. On the other side, or the destination side of the tunnel, which is router 2, their IPv4 address is 192.168.30.1, two different network, right? As long as from tunnel source, which is our router 1, and tunnel destination, which is router 2, they can ping each other on IPv4, I'm ready to create the tunnel. Simple as that, right? So on R1, interface tunnel 0, right? So tunnel source is 192.168.99.1. Tunnel destination is 192.168.30.1, which is this. I can ping them before I tested it, right? Tunnel mode is IPv6 IP. So that's what the simple configuration of the tunnel. When the tunnel is configured, then afterward, you need to kind of specify a v6 address on top of the tunnel for the peering. Why we need the v6 address? Because when you create the tunnel, it's a virtual interface, right? And then you see between R1 and R2, the virtual interface will work like a point-to-point network. So on the point-to-point network, we need to specify a v6 address, right? And on that v6 address, that's supposed to be in the same subnet. So that's what we have. Like point-to-point network should be in the same subnet. 2001 DB8 C18 colon 1 colon 64 colon 64. So colon 3 in this side, colon 2 in this side. So that's what IPv6 address configuration. Then what do you do? When you finish this configuration, then you will see your tunnel is up, right? And from this side, if you ping on the IPv6 address colon 2, you can ping. And from the other side, if you ping colon 3, you can ping. So when the tunnel is up and on the tunnel interface you can ping each other, then you are ready to create your BGP peering if you have a BGP, right? When you create the BGP peering, then two sides can exchange their LAN IPv6 address in BGP. Make sense? So that is what the concept of manual tunneling. Any questions so far about the manual tunneling? If not, then you can move forward. Now we'll see 624 tunnel. So 624 is an example of automatic tunnel, right? And in automatic tunnel, what we defined, tunnel source is configured manually, but tunnel destination is not configured the way we did in this previous example. Tunnel destination is configured already, but in the automatic tunnel, no, we don't configure tunnel destination. That will be discovered automatically, right? Let's see how router can discover tunnel destination automatically. Say 624 is a special type of network. 624 is a special type of network where we have a special community people who are 624, like the academics. Say for example, academics or any group of people. If they have IPv6 supported machine, on the other side of the internet, there is a community who also support IPv6. So those two networks on the edge of the internet want to communicate or would like to communicate in IPv6, right? This is just a private communication in between them. If they want to do that, but they are upstream to whom they are connected to, they are not ready yet to forward traffic on v6. That is the situation. To solve this type of situation, this technique 624 tunnel can be used. Both sides of the network, they are ready to use IPv6 as a protocol, but in the middle, the internet infrastructure doesn't support it. They are not ready yet. So what these two community or two group of people can do, they can use a special address allocated by IANA or IETF. They standardize this address for this 624 tunnel encapsulation, automated tunnel encapsulation, which is 2002 colon 16. So that is what special address allocated for the 624 sort of tunneling, automatic tunneling. So in this sort of tunneling, the concept is you have a special address reserved for that 2002 colon 16, right? So every network who want to communicate with other side who runs IPv6, they use this special address 2002 colon 16, and then afterward they will embed, they will incorporate their v4 address inside that. So now the question is how they will do that. v4 address, how many bit? 32 bit. Say for example, this router loopback address, whatever the loopback address they use, right, on that router in v4, that 32 bit address can be converted to binary and then convert it back to hex, right, and put it here. So this is how this network will have their LAN IPv6 address. Start with 2002, which is 16-bit. Then the loopback comes here, 32-bit. 16 plus 32, 48-bit address in IPv6. So if you see the whole 48-bit, out of the whole 48-bit, first 16-bit is fixed. Then after 16-bit up to 48-bit, what we have is IPv4 address encoded, inbuilt. So every site around the world who want to communicate, they will build their LAN IPv6 address in that way. Say for example in this site, they have their loopback. What they did on that loopback, they converted this into binary and converted it back to hex. So this is what their IPv4, IPv6 LAN address. If you see their IPv6 LAN address and their IPv6 LAN address, both LAN address has got IPv4 address inbuilt inside. Make sense? Then what they do, they'll do this simple configuration on the router 2 or router 1. What configuration? Tunnel interface 10, say for example no IP address, IP number Ethernet. Tunnel source is loopback. Tunnel destination is, or there is no tunnel destination, sorry. Tunnel mode is IPv6 624. And if you see the configuration, they only specify tunnel source in the configuration. Same configuration can be done or need to be done by the other routers or all the 624 routers. So what we have, we specify tunnel source, but we haven't specified tunnel destination. But we specified tunnel mode IPv6 IP624. And then afterward, they have added a static route in there. What static route? Anywhere 2002:16, right? For example, it means all the 64 site everywhere in the world, because every 64 site around the world will have the same /16. That will go through tunnel 0. Okay, if this is the case, now what happened? So from this side, anyone want to browse a host on the other side, right? So that address will be learned by DNS, right? So what he knows about the other side, 2002 C0A8 6301::1, say for example, a machine that he want to browse. When the destination packet comes here, he need to create the tunnel now. So when he will create the tunnel, so what he will do, he will see a match of the destination 2002, right? /16 tunnel 0. He will come to the tunnel 0. And on the tunnel 0, source is loopback. On the IPv4 header, they will specify loopback as a source. But there is no destination of the tunnel. So what they will do, since it's 624 encapsulation, from the destination address, they look into those bits 17 up to 48, take it out, convert it to dotted decimal IPv4 address, and that address will be put it on the tunnel destination in here. So this is how we have a v4 packet. Now you see this packet will be forwarded up to other side using v4. This is how I got the destination side of the tunnel. So it's a very clever way to manage or solve this issue, solve this problem. So that's what we call 624 tunnel, where tunnel destination is discovered automatically. When the packet goes, now the reply packet, same way, on the reply packet, source is this v6, right? So this v6 address is already inbuilt within that encapsulation, right? So they will know the destination as well. So when they will create the destination side or return packet, so they will take that destination address like bit 17 up to 48, and that will be added on the tunnel destination from this router. So this is how 624 tunneling will work. Make sense? Any question? Okay. So we saw how 624 tunneling works and how 624 solve the automatic discovery of the tunnel destination, right? Now the question is, okay, in 624, what we solve, 624 site can browse to a 624 site. Only 624 site can browse or access to a 624 site. What about 624 site would like to access a native v6 site as well, right? So the configuration that we saw in the previous slide, a 624 site can only access to a 64 site, but a 624 site cannot access to a native v6 site. So if a 624 site want to access a native v6 site, how they can do that? According to the previous slide, no option, no way. That is why we have another technology, another concept called 624 relay, right? 624 relay. What that 624 relay means? 624 relay means whoever in the world running a 624 site, they are connected to a native site now, right? So they have got, or anyone in the internet has got connectivity to a 624 site plus a native site, they can deploy a service called 624 relay. So when they will deploy the service called 624 relay, then through that relay, from other side, anyone is running only 624 can come to that relay router, and from that relay router, packet can be forwarded to a native site or a 624 site, right? Let's see how it works. Whoever would like to run a 624 relay site, for those operators, there is a special address by IETF, by RFC 3064. So that Anycast address is 192.88.99.0, right, in IPv4. What they will do, they will run an Anycast, all those 624 side, or all those 624 relay side, they need to run an IPv4 Anycast, which is a special address that is 192.88.99.0. How they will do that? They'll configure their loopback with, or they'll configure another loopback with this special address 192.88.99.1, say for example, right? So if there are 10, 20, 40, 50, hundreds relay routers, all those relay routers will use the same IPv4 address 192.88.99.1 on a loopback, a different loopback, right? And then they will announce that /24 Anycast block to the global internet. When they'll announce it, then you will see in the whole world or whole internet that Anycast address is available. Now the point is, from this part of the world, from Australia, if I need to see the nearest Anycast, that could be somewhere in Australia, somewhere in Brisbane or Sydney. But if someone is looking at from India, their nearest one could be somewhere in India, right? Not probably the one in Australia. So relay router, they can find from the nearest relay router by using the routing protocol, because that's announced from BGP anyway. Then what they will do apart from that, simple configuration, they just add a static route, IPv6 route, ::/0. It means everywhere or everywhere they want to go, apart from the 64 site, which is 2002. And they will use 2002 and then : this 32-bit is actually converted from that Anycast address loopback you just convert it to binary and then put it here. Then what will happen? If any 64 site want to browse any native site, so this is the match. On this match, this is the next hop. On the next hop, tunnel destination is incorporated, inbuilt, right? So this is how the tunnel packet will be created with the destination. IPv4 address is this. Then on IPv4, they will find out the nearest relay router, either in India or in Australia or in Japan, and they will forward it natively from there. Make sense? Any question about that 624 relay? Okay, if not, then we'll move forward. So that you can see in the internet, there is a special address I told you for IPv4 Anycast for 64 relay, which is 192.88.99.0/24, right? And you convert it to binary and convert it to hexadecimal. So this is what the gateway or next hop will be used by every 624 site if they want to use the relay service. Simple as that. Make sense? So that is what sort of a configuration of the relay router in 624. So loopback configuration and their tunnel configuration, interface configuration, and on BGP they announced their Anycast network, and just they added the network in IPv4. So sorry, in IPv6 they advertised the 624 address as well, and then they create the static route. That's it. Make sense? Okay. Now we will discuss about 6RD. This is another technique. 6RD conceptually same as 624 relay or 624. Conceptually same. Tunnel destination will be discovered automatically. But in a real environment, in which situation we use 6RD tunnel? In such a situation where my customer network support IPv6, my transit ISP support IPv6, but my backbone, ISP backbone, doesn't support IPv6 unfortunately. So for example, my BRAS, I cannot upgrade my BRAS because it's very, very expensive investment for my network. Right? My PPPoE server doesn't support IPv6 authentication. What I do? My customer is ready, my upstream is ready, right? But I cannot apply IPv6 into the customer network. So that is the solution that you can use, 6RD, rapid deployment. That's what France Telecom, their brand, like free, they did it. So they did it successfully. Then afterward, some other operators, they also deployed 6RD as well. The downside of 6RD is the customer CPE need to have 6RD support as well. You can't just use any CPE. CPE need to have a 6RD support. How 6RD works? As I said, in 6RD, conceptually is same as 624. The difference is in 624, you need to use the spatial address 2002::16. But in 6RD, no. You use your own prefix given by the registry. So for example, you receive a prefix from the registry 2001:db8::32. This is what your own prefix. By using your own prefix, you want to deploy IPv6. What do? You create your site address, this individual site address or customer address, by adding their point-to-point link from your VRAS or from your JSLAM up to the customer point-to-point link. You use V4 address. That V4 address, 16-bit of that address, you put inside IPv4 address. When you put the 16-bit, not from the first part of the network, like not the network part, from the host part, because most of the case network part will be same, but host part will be different for different point-to-point link, right? So that host part will incorporate inside. Then what will happen? From here, when they will create the tunnel, right? Tunnel destination, they will see the tunnel destination is already inbuilt with the site address from 32 up to 48. 16-bit already inbuilt. So they'll take the 16-bit out from that encapsulated address, right? And then they'll use that one as a tunnel destination from relay server up to the other side. Make sense? So this is how 6RD tunnel works. No difference than 624. Exactly same. Only the difference is in 6RD you use your own prefix, and when you encapsulate your V4 address, go and get the host part of it, not the network part. Make sense? Tunnel broker, I've already explained what is tunnel broker, right? In a tunnel broker network, you manage only one tunnel up to the tunnel broker, and from your network up to the tunnel broker is manually configured. That's what we call semi-automated. And when it is configured on the browser, right, then these configurations are uploaded on the tunnel broker routers, the POP routers. So the tunnel between your network and up to the tunnel broker POP is sort of a manual tunnel. From there onward, when it goes to the customer side, it's all either native or again there is a tunnel. So that's what we call tunnel broker. So transition strategies, what you can do. So when you do IPv6 deployment into your network, the best way is all your old customers, they will have V4 address. New customer, when the new customer comes, you don't have any V4 address, either as a customer or as a server. So what do? You use carrier grade NAT CGN, and you also use IPv6 on the customer side. So when you give prefix to your customer on V6, give them global IPv6 address from the DHCP v6 server, right? And when you give address for the IPv4 stack, give NATed address. So that's how you can scale, you can grow, right? So now your customer network, they have got both V4 and V6. V6 is end-to-end global IPv6 address, and IPv4 is NATed private address. So this is how you can build your customer network. Then we have address family translation. So I have already explained all those terminology, what is dual stack, what is IP in IP tunnel, right? And address family translation. So there is a concept, we can do translation from IPv4 to IPv6, right? That's what we call translation. Some of the telcos, they actually deploy these things. They use NAT64 and NAT46. So when they use NAT64, it means on the customer side, they have got IPv6, and when the IPv6 only customer want to browse IPv4 side, there will be an ad. So when they will browse IPv4 side, how the name resolution will be working, that's why we need to deploy DNS624 as well. Okay, so this is how all those transition technologies can be used and all those terminologies are used. So that's it. That's the end of the presentation for today. We just gave you some ideas what are the transition technologies currently available and how we can use it. So hope the session will be useful. Before we wrap it up, is there any question from the participants? Do you have any question? We have a couple of minutes for the question and answer. And also, like you will see, we have a feedback in here, feedback URL. The URL is surveymonkey.com/a/pnic-2013-0306-EL3, right? We really appreciate if you can spare some time and give us some feedback, because your feedback is very important. This is how we will try to improve our future e-learning session. Okay, so when you will finish the survey, then the URL will direct you to an FTP site. From that FTP site, you can download that presentation that we did today. Okay, so is there any questions so far? Okay, if not, then thank you very much. Hope the session will be useful for you. And oh, there is a question. 2002 is fixed for tunnel. If next certificate will send, what happened? Okay, the question is 2002. Are you talking about 624 tunnel, right? So automatic tunnel. 2002 is fixed, which is 16-bit for the tunnel. Next 30-bit will be same. How next 30-bit will be same? Because in the global internet, different operators, they have got their unique /32 in IPv4. We are talking about internet. So every internet has got their own /32 unique. So for example, ISP in X, whatever the loopback address they are using on their gateway router, definitely will not be same of ISP Y router's loopback. It will be different. So that is why the last 32-bit will cannot be same all the time. Make sense? Okay. Is there any other question? If not, then thank you very much, and keep your eye on in our e-learning webpage, which is www.epinic.net/elearning, and we have published all our e-learning schedule in 3 months ahead. So all those schedule that we have in next 3 months are already published. If any of the topic that is interesting you, just go and register for that and make yourself available on that particular day. Okay, so it seems server URL is not working. Oh, is it? No, it's working. Okay, I'll write down the URL in here. www dot surveymonkey.com/s/a/pnic20130303. Okay, that's the URL. Should work. check the site. Yeah, that's fine. The site is working. I just clicked here and it took me to e-learning web page. I'll just copy and paste it for you.